So abhi we did an example where we saw how all of our kinematics, kinetics, and universal laws tie up together because of once we know the constitutive material behavior, right? So now let's see कि इसी को अभी हमने जो स्टेप वाइज किया था, we found displacement से strain से stress and so on. Is it possible for us to combine all of this up together ताकि वो जो मैंने आपको कहा ना full circle आ गई बात कि kinematics, kinetics, universal laws, how they're gonna play a part for one particular material. So let's see how we can combine them all up to get something a little bit more straightforward, given that we already know the material that we're dealing with. So as you guys know, we're talking about the elastic solid, but in particular for the elastic solid, we're also being very precise, and we're talking about the isotropic elastic solid. ठीक है जी, isotropic linear elastic solid. So for this, let's try to, as I said, tie it all up together. Perfect. So for that, I need to go back a little bit to our kinematics. और अभी मैंने example में भी थोड़ा सा brush through कर दिया था, और उसको थोड़ा हम और elaborate करते हैं कि पहले भी हमने इस चीज़ के बारे में बात की थी कि when we're talking about linear elastic materials, most of the time we're talking about small strains. ठीक है जी. Or there is as we discussed, there is a reason for it, because physically in the real world, linearity and elasticity are only applicable when we have just small deformations. उससे ज़्यादा large पे जाते हैं तो फिर materials जो हैं real world materials, they no longer behave in an elastic linear manner. ठीक है, एक ये वजह है. दूसरा ये वजह है which you will see now कि why we are going to be assuming the infinitesimal deformation. और इसी से the word now that we are talking about when we're tying all of this up together is that we are starting to define this theory of elasticity for the small strain regime. That is, we're looking at the infinitesimal theory of elasticity. Now let's see why there's a very useful thing related to small strains. One is कि if you notice कि if we are just having very small deformations, मतलब ये है कि एक particle जब deform हो भी जाए तो वो अपनी vicinity के अंदर ही रह रहा है, बहुत ही करीब. So one main thing that comes out of it for solid mechanics at least, because we small deformations हैं, is कि हमारी Lagrangian और Eulerian description के अंदर कोई difference नहीं रहता. That is because our particle जो original position था उससे बहुत ही कम displace होता है. That is, अगर वो पहले जिस तरह हम define करते थे, अगर वो पहले यहाँ था reference में और अब वो उठ के इधर से इधर चला गया हल्का सा, right? Then we can carry on considering that this is still, so to speak, as if it's in its reference configuration. That is, as I said, our small xi becomes approximately equal to our capital Xi, right? Because we are in our infinitesimal deformation. Next then, अगर ये assumption हम कर रहे हैं, that is small strain में है, फिर उसकी वजह से और भी ढेर सारी बहुत ही खूबसूरत चीज़ें आनी शुरू हो जाती हैं. The first of which is कि हमारे जो gradients थे space में वो simplify होना शुरू हो जाते हैं. Because you might recall कि we had kept a distinction so far. We knew कि हमारा जो displacement gradient है वो तो with respect to capital X है, लेकिन जो हमारा velocity gradient है वो तो with respect to small x था. लेकिन इस केस में when we are in our infinitesimal theory of elasticity, when our small xi and our capital Xi are equal, then there is no distinction between these either and they become interchangeable. Of course, इसी से एक और फिर खूबसूरत चीज़ निकलेगी, which is कि now our material derivative, मतलब ये तो space का gradient था ना, now our time derivative, the rates of change, they become simplified as well. And we no longer have to use that long-winded chain rule, but instead in this case, our material derivative is actually equal to the time derivative at a spatial position, basically. So this assumption of the infinitesimalness of deformation simplifies things considerably, as we shall now see, in tying up our kinematics, kinetics, and our universal laws for our linear elastic isotropic material. So let me write down all of those things that we've discussed so far, just so that we can summarize them right here. So first of all, we saw how from our kinematic analysis that we know how the, क्योंकि हम small strain में, as we just discussed, we know how the small strain tensor is related to our displacement gradient. ठीक? Now the nice thing is that हमारा displacement gradient जो है, which was originally with reference to del naught, that can actually be replaced. मतलब वो ये था ना, capital J के लिहाज से था, because it was capital X के लिहाज से. This was del by capital X. But as I've just discussed, this can now be replaced with our small x, such that हम अपने small strain tensor को लिख सकते हैं in terms of the spatial positions. ठीक है, और यही हम करते हैं जब हम अपने जब हम अपने मटेरियल के स्ट्रेन्स को डिफाइन कर रहे होते हैं, राइट? हम उसको भूल जाते हैं कि वो उसका कैपिटल एक्स है या स्मॉल एक्स एंड सो ऑन, बिकॉज इट्स ऑल द सेम essentially. Okay, so that's just a recap of our strain displacement relationships. Next, we also remember, I hope, that there is another condition that is required for the small strain tensor, and that is the condition of compatibility. ठीक है, which is that we know, हमने discuss की थी इसके बारे में in length, के compatibility का physically मतलब क्या है. इसका basically मतलब ये है कि अगर हमारे पास कोई strain field है, so we just want to make sure कि if I have a body like so and then I'm defining a strain field, let's say उसका इस part पे ये strain है, इस part पे कुछ strain है, इस part पे कुछ strain है, and so on, we're just trying to define कि it should all fit together nicely. It shouldn't be कि इस strain field की वजह से हमारे particles actually इस तरह deform कर रहे हो कि ये यहाँ रह जाए और इसका neighboring जो था वो कहीं यहाँ पहुँच जाए, such that अब कोई gap बन गया है continuum के अंदर, because this is just not possible in our continuum description. That is, we need to make sure that our strain field is physically compatible. और फिर उसकी हमने maths की भी discuss की थी. I don't want to go into a repetition of what we've discussed. So if you don't remember what the compatibility condition was, please go back and refer to that lecture. It was either lecture 4 or lecture 5 when we were talking about the kinematics of continuum media. But the point is just कि हमारे पास एक और condition है on strain. Or the only important thing to note about this is that this only comes into play when we already know the strain field and we are trying to find the displacement field. Okay, so इसके लिए सिर्फ हमें ये चीज़ याद रखनी है, ठीक है, कि what if somehow we applied, let's say, force sensors on our body और उससे हमने किसी तरह internal stresses determine कर ली हो for our continuum body. So stresses निकल गए तो Hooke's law लगा के हमने strains निकाल लिए, तो अब जो strain से अगर हम displacement निकालने की कोशिश करेंगे तो फिर हमें ये compatibility लगानी पड़ेगी. ठीक है, it's always when we're going from strain to find displacement when this comes into effect. Otherwise, we don't need this condition. Okay. So next, we have already also just developed our constitutive equation. That is, we now know कि किस तरह हमारे strains are related to the stresses. ठीक है, तो ये मैंने बस वही उठा के वैसे का वैसा लिख लिया है. Please note कि हम इस खास material की बात कर रहे हैं, linear elastic isotropic material. ठीक है जी. Now finally, there is also, as we just considered in our previous example, there are universal laws which are applicable for this stress field, In particular, as I discussed, the stress field pops up in the first law of thermodynamics and in the equation of motion. So if I just write that down here and see that now we have another expression जिसमें perhaps we can then combine these two. एक तो चीज़ अभी नज़र आ रही है, अभी देखते हैं इसको, लेकिन पहले मुझे ना इस इक्वेशन ऑफ मोशन को थोड़ा सा और ज़रा मैनिपुलेट करने दें. So इंडेक्स नोटेशन में of course it is just this. ठीक है जी, जो divergence of sigma is, as we've noticed before, it's this expression. It's one inner product. Okay. So because of our small strain assumption, as we've just seen, the material derivative becomes the same as the, well, एक second, sorry, let me think about what I'm trying to do here. Yes, sorry, got it back. So let me just consider what the acceleration is. Okay? So acceleration, we know it's just the material derivative of velocity, or velocity is the material derivative of the current position, right? So it's just this expression. लेकिन अब मुझे आप लोगों को ये याद कराने दें कि we also know कि how these are related in terms of the displacement, right? So the current position is related to the displacement and its original position like so. मतलब ये कि अगर मैं इसको differentiate करूँ तो reference position तो वैसे ही it's a fixed, it's a constant. So I can convert my acceleration expression in terms of displacement. This is just unnecessarily complicated, but what I'm just trying to point out, as I think you all know, that the velocity is the rate of change of position, या फिर it's the rate of displacement, और उसका derivative जो होगा वो of course will be the double derivative of the displacement. That is, and I know I think I just missed this out. I should have brought this up way earlier जब हमने acceleration को introduce ही किया था कि acceleration can actually be written down in terms of the displacement as well. So just think about this for a second. This is not rocket science at all. This is actually 8th class level thing that we're talking about, which is we know the velocity is what? It's the rate of change of, it's the rate of displacement. It's u dot, right? So अगर इसी का मैं इसका derivative ले रही हूँ acceleration find करने के लिए, then it's just acceleration is u double dot, right? और उसको maths के तरीके से अगर follow करना है, so we can do this. Could someone please confirm कि this is clear, कि the acceleration is just equal to this thing? Anyone there? If no one responds in the next 30 seconds, I'm going to stop class here and then I'm not going to have any classes for this course. Yes.
It is clear.
Okay, thank you. How hard was that? Come on guys, please. Okay, so as I said, I should have brought this up earlier, but I forgot. So just right here, see if we can write down the acceleration in terms of the displacement. ठीक है Adnan, thank you. Okay, so अब देखते हैं कि what have we got. We have our equation of motion in terms of the displacement. I know what my strain is in terms of the displacement also, and I know what my stress is in terms of the strain. So why don't I pop this one in here and then this one in here? मतलब ये कि वही जो भी हमने एक एग्जाम्पल सॉल्व की थी वो इक्विलिब्रियम चेक करने के लिए या फिर इक्वेशन ऑफ मोशन में स्ट्रेस फील्ड को डालने के लिए, starting from the displacement field, why don't I actually just combine all of this up, combine all of these kinematics and kinetics and the physical laws all into one? That is, I take my equation of motion this is my equation of motion, and I substitute in here my constitutive law. That is, ये जो मेरा सिग्मा है, इसके लिए मैं अपना constitutive law, मेरा Hooke's law for my linear elastic isotropic material, I pop that in. Clearly what is happening, it's sigma ij differentiated with respect to j, so sigma ij की पूरी expression डाल दी with respect to j. ठीक, फिर क्या करते हैं, फिर ऐसा करते हैं ज़रा और थोड़ी, अभी already complicated enough नहीं थी तो और हम कर देते हैं. Why don't I replace the strain with my displacements? That is, I substitute in my strain displacement equation in here. Now see, epsilon ij की जगह I've just popped this expression. If you guys take your time slowly when to follow के, it's easy to do this because we've got index notation. ठीक है जी, so for example इधर if I've got
तो वो कैंसिल हो गया, ठीक है मैम, ओके.
Yep, so 2 और हाफ कैंसिल हो गए. इधर क्या होगा, इसके बारे में आपको सोचना पड़ेगा. एप्सिलॉन के से हमारे पास क्या आएगा कि आई जे की जगह, दोनों की जगह के और के डल जाएगा, सो दैट वील एंड अप विद जस्ट यू के. सो दैट्स व्हाई आई हैव गॉट माय यू के कॉमा के. ठीक है, प्लीज नोट कि वो 2 और 2 इधर कैंसिल हो जाएगा एप्सिलॉन के अंदर, बट एज फॉर द लेफ्ट हैंड टर्म वो 2 इधर से कैंसिल हो रहा था. ओके, नेक्स्ट नाउ ऑल दैट्स लेफ्ट इज, इसमें अभी से हम नोट करना शुरू कर सकते हैं कि अब हमारे पास सिर्फ वो स्ट्रेस और स्ट्रेन सब गायब हो गया, सिर्फ डिस्प्लेसमेंट रह गई है. तो लेट मी, लेकिन थोड़ी कॉम्प्लिकेटेड लग रही है, सो लेट्स जस्ट सिंप्लीफाई दिस अ लिटिल बिट फर्दर. और अब ये एक एक स्टेप, इट्स जस्ट इंडेक्स नोटेशन की सिंप्लीफिकेशन है. आई वी आर गोना स्किप दिस बिकॉज, जी रबिया. Sorry, Rabia, I didn't catch that.
Ma'am, can you please explain again that how we've got this UKK?
UKK, okay. So check here that if I take my epsilon's expression and if I have epsilon KK, मतलब ये कि जहाँ पे I है जहाँ पे J है दोनों की जगह K डाल दें. So let's see what happens. That becomes half U K comma K, right? I B K, J B K plus U K comma K again. So that is 2 UK comma K जो half से cancel हो जाएगा. That's why epsilon KK is directly just equal to UK comma K. Rabia?
Yes, ma'am. Thank you so much.
No problem. Okay, so now as I was saying, after that it's just the case of index manipulation. ठीक है जी. So इसमें कोई फिज़िक्स नहीं आ रही. अभी तक हम फिज़िक्स की बात कर रहे थे, राइट? हम कोई फिज़िकली कोई चीज़ें कर रहे थे एंड इट वाज मेकिंग सेंस कि हमने कंस्टिट्यूटिव लॉ डाला और फिर स्ट्रेन डिस्प्लेसमेंट इक्वेशन. लेकिन इसके बाद जो ना इट्स जस्ट index notation manipulation. So I'm going to skip that because that does not help us very much physically speaking. But the only thing is we do need to be pretty comfortable with index manipulation. But the point is कि we can rearrange it, simplifying. सिर्फ क्या हो रहा है, ये जो कॉमा जे था उसको अंदर ले जाएं, फिर ये डेल आई जे जो है डेल्टा आई जे उसको सिंप्लीफाई कर लें एंड सो ऑन. राइट नाउ वी आर नॉट इंटरेस्टेड इन दैट पार्ट. ठीक है, so just note that when we rearrange it, we can get a slightly, I'm not saying it's overly simplified, but a slightly more simplified expression which essentially consists of these three things combined together. It consists of the equation of motion, in जिसके अंदर we've popped in the constitutive material behavior of an isotropic linear elastic material, and finally within which we've substituted our expression for strain and displacements. Now the important thing about this, let me elaborate just ताकि हमारी नज़र में सिर्फ ये हो बाकी सब कुछ के बजाय, इसके look carefully at it now. The only variable, so to speak in this. अब देखते हैं ज़रा कि क्या हो रहा है एक एक टर्म को. Mu is the material का material parameter mu जो Lame's constant का था. Okay, good. फिर क्या आ गया, सिर्फ u रह गया variable. इधर क्या है, इधर we have mu and lambda, again material parameters, so the only variable is u. And then finally rho, again a material property, but then of course body forces कि क्या loading या क्या उसकी situation है. So that's fine, that this is still perhaps an unknown, या perhaps it's a known boundary condition depending on what physical problem we have. And then finally on the right hand side we just have a variable in u. The point being that we've combined it all up together to get a differential equation. Now please note differential equation, why? Because this is a derivative with respect to time. There's also these derivatives with respect to position or with respect to space. So there are derivatives in here. So this is a differential equation, but with only ignoring the body forces. Let's assume कि हमें पता है, ठीक है, body forces क्या हैं, हमें एक problem, physical problem है हमारे पास. So then the only variable in here is just displacement. So then it's just a differential equation in displacement, or all that we need to do to figure out कि उस material का क्या behavior होगा for a given problem is to figure out how to solve this differential equation. और उससे हमें पता चल जाएगा. So this is a pretty neat thing, because we have converted all of our knowledge of kinematics, kinetics, universal physical laws, and the particular behavior of the elastic, linear elastic isotropic solid to just get one equation that we can then, और अगर हमारे पास कोई particular problem हो तो हम उसको solve कर सकते हैं उसके लिए. अभी मैं इस चीज़ के बारे में ज़रा, give me 1 minute and I'm going to start to discuss कि what do I mean कि we can solve it and we can have, for a particular problem we can solve it and so on and so forth. पहले there's just a little bit of more.
मैम
जी.
जो आप आज लास्ट एग्जांपल करवाई है उसमें आपने बताया था कि हमें साथ साथ जो है ना वो फिजिकल लॉज को भी इम्प्लीमेंट करते जाना है.
जी.
तो अच्छा नहीं है कि ये एक इक्वेशन से हम जो है ना, क्योंकि इसके अंदर इक्वेशन ऑफ कंटिन्यूटी भी यूज हो रही है, तो हम इसको ही खाली एक को ही ट्रीट करें, इसको ही इम्प्लीमेंट करें. बिल्कुल.
So that was the purpose of that. This is the purpose of doing this. यही हम कर रहे हैं कि बजाय ये कि वो तीन अलग अलग पड़ी हों और हम एक एक करके कर रहे हों, we should just be able to combine them all together into one. Exactly right, Matab. Take. So just to clarify here, as I always say कि tensor notation से के अंदर लिखने से ना कुछ information lose हो जाती है unless you are very confident in tensor notation और आपको पता है कि del squared का मतलब क्या है. और ठीक है, कुछ लोगों को पता होता है, sure, if they've seen it so many times. Sorry, Matab, please keep your mic muted. That this del squared is the Laplacian operator. ठीक है जी, उसका नाम है, जिस तरह ये del operator था, del का जो squared है उसका नाम है Laplacian operator. लेकिन for the life of me, I am unable to memorize these things, right? So what I like is the index notation, because with that, guys, please keep your mics muted. So क्या हो गया? Numan, is everything okay? Numan ने कर दिया. Okay. So so that's why just as I said, I will always provide you both of them, because in my opinion, the index notation offers so much information that it's just very useful to have it in here. So just to clarify with that कि ये जो Laplacian operator है वो है क्या चीज़, उसके अंदर क्या है? It is ui, jj, ठीक है? So jj is the dummy index. So differential के ऊपर dummy है. So then बस then it's a matter of expanding out. हमने I think हम index notation में अब इतने तो comfortable हो गए हैं कि हम ये कर सकते हैं. ठीक. So it becomes u1 का second differential with respect to x1 का squared plus u1 का ही second differential but this time with respect to x2 plus the differential with respect to x3 and so on. And the secondly, on this middle term, we have it's worth seeing what's happening here. So this del dot u, it's u ka dot product with the del operator. If you guys recall, this thing is known as the divergence of u. ठीक है, जिस भी चीज़ का कभी भी डेल डॉट हो रहा होता है ना, वो डाइवर्जेंस होती है. डॉट प्रोडक्ट विद डेल इज द डाइवर्जेंस. और फिर वो डेल से मल्टीप्लाई हो रहा है बट नॉट एज अ डॉट, मतलब वो जस्ट नॉर्मल मल्टीप्लिकेशन. सो दिस इज जस्ट देन इसको आई थिंक वर्थ जस्ट एक्सपैंडिंग आउट. सो दैट इज इन इंडेक्स नोटेशन इट्स दिस वन, और उसको अगर एक्सपैंड करके लिखें तो वो ये चीज़ है. नाउ आई नो कि दिस still seems pretty complicated और है, no doubt about it, but then material behavior पूरा हम analyze करने की कोशिश कर रहे हैं. So yes, और इसीलिए even if we jump directly to this equation and use it, it takes a while to solve by hand क्योंकि we have to figure out these different terms, right? लेकिन आपने देखा था कि अभी जब मैं पीछे वो एग्जाम्पल में कर रही थी तब भी मुझे आई वॉज ट्राइंग टू बी एज फास्ट एज पॉसिबल बट स्टिल इट टुक मी सम टाइम टू फिगर आउट के ओके गिवन डिस्प्लेसमेंट फील्ड से स्ट्रेन क्या निकल रहा है, उससे फिर स्ट्रेस क्या निकल रहा है एंड सो ऑन. सो इट्स जस्ट नॉट दैट स्ट्रेट फॉरवर्ड. ओके, नाउ लेट्स जस्ट having looked at the technicalities, just discuss this वही again के importance क्या है in equations की. So first of all, this is basically defining, ये जो equation है ना, this is defining the this is defining the infinitesimal theory of elasticity जो हमने नाम से शुरू किया था ना. This equation is the backbone of it. ठीक है, और इसीलिए again it has a name as well. It's known as the Navier equations या फिर the Navier-Lamé या फिर Lamé-Navier equations. Please note उसके अंदर Lamé is constant आ रहे हैं, that's why. और I know this might seem very familiar, right? I hope that this name rings a bell. So many of you may have heard of the name Navier-Stokes equations. और वो क्या थी? Navier-Stokes equation was the exact equivalent of this for Newtonian fluids, for a special type of fluid. So my point just is कि जिस तरह Navier-Stokes equation पे हम arrive करते हैं ना for fluids, that is we combine kinematics with kinetics with universal laws for the constitutive material behavior of those simple fluids, उसी तरह ये Navier साहब ने ही derived the equation governing the linear elastic isotropic solid. And as I said, the beauty of this is that it is an equation with just one variable u, and we can solve it to figure out के एक particular problem, एक particular loading, एक particular scenario के लिए how would that solid behave or how would that solid deform essentially. Okay, so अब let me discuss कि ठीक है हमारे पास ये equation तो आ गई लेकिन what do I mean when I say कि एक particular problem या particular situation या loading conditions की बात करते हैं. So what I just mean by that is कि जिस तरह हमने कहा था कि आपने undergraduate में एक beam को लिया था, उसको आपने uniaxial behavior किया था, फिर आपने उसी beam को लिया था, उसकी bending देखी थी या उसकी torsion देखी थी या so on. The point is, depending on what the loading is, या फिर in other words, more technical terms, depending on what the boundary conditions are, we can solve this equation to figure out कि okay, उस केस में उसकी डिस्प्लेसमेंट क्या होगी. So these boundary conditions together with this Navier-Lame equations are known as a specific boundary value problem. I'll come to this just now. That is, we can solve, as I said, we can solve this equation given for different boundary value problems to figure out कि क्या deformation या displacement होगी for that case. Whew. Okay guys, just a few more moments. The example I'm going to skip, we'll come back to this next time. I just want to carry on just the conceptual discussion for a little while longer. हाँ जी.
ये भी सुना था जब भी कभी फ्लूइड की क्लास हुई होती थी हमारा कोई लेक्चर इस तरह आता था तो उसमें ये भी बताते हैं कि नेवियर-स्टोक्स इक्वेशन को इसका एक तो एग्जैक्ट सॉल्यूशन नहीं एग्जिस्ट करता और सेकंड ये इसके डेरिवेटिव्स को सॉल्व करना बहुत मुश्किल होता है लेकिन अभी तक तो ये लग रहा है कि इजी है.
अभी देखते हैं इसके बारे में हम डिस्कस करते हैं. So let's just wait for a little while about this. Okay, how do we solve the Navier-Lame's equation? Just a moment. Okay, let me just define it completely. Okay, we need the equation, but on top of that we need the boundary conditions. ठीक, क्योंकि जब हमारे पास कोई specific boundary conditions होंगी तो फिर ही हमारे पास it's a differential. You remember differential equations को जब हम solve करते हैं तो हमें कोई बाउंड्री कंडीशंस चाहिए होती हैं ताकि हम वो कांस्टेंट्स ऑफ इंटीग्रेशन को निकाल सकें एंड सो ऑन, राइट. So that also applies for these extremely complicated differential equations, that we need some boundary conditions to be able to solve them, right. So now comes this point कि when you have those boundary conditions together with the Navier-Lame's equations या फिर for the equation for the infinitesimal theory of elasticity, together those two are known as boundary value problems. और बेसिकली बाउंड्री कंडीशंस जो हैं वो हमारे पास डिफरेंट टाइप्स की हो सकती हैं. सो फॉर एग्जांपल यू नो व्हेन आई वाज टॉकिंग अबाउट यूनी एक्सियल डिस्प्लेसमेंट, सो आमतौर पे उसमें क्या किया होता है कि हमने फिक्स किया होता है अपनी बीम को और फिर हम इधर से पुल कर रहे होते हैं, राइट. सो इन दिस केस क्लियरली वी आर अप्लाइंग कोई डिस्प्लेसमेंट हमने बाउंड्री कंडीशन लगाई हुई है कि इस एंड पे ज़ीरो डिस्प्लेसमेंट होनी है और इस एंड पे मूव करना है जितने से भी मैं अपने क्या कहें ग्रिप को मूव कर रहे हैं. So that is, this type of boundary condition is one where we only have displacements being specified, so it's known as a displacement boundary condition या displacement boundary value problem. इसी तरह हमारे पास this should be इसी तरह we can also have cases when instead of the displacement we have the loading being specified. मतलब ये कि हम उसके ऊपर जो stress apply कर रहे हैं on the surface या फिर in other words जो traction हम apply कर रहे हैं या फिर the force per unit area that we are applying on the boundary, so that then becomes the traction boundary value problem. या इसको force boundary value problem भी कहते हैं, no problem, that's also fine. Traction is just the force per unit area from the external system. So this one then would be known as the traction या force boundary value problems. But most of the time we have mixed boundary value problems जिसके अंदर हमारे पास कुछ part पे displacement prescribed होती है और कुछ part पे traction described होती है. Okay. So just noting that these different boundary conditions that we can have. Now let's jump to discussing how do we solve them. As Mahtab was pointing out कि Navier-Stokes equation तो next to impossible होती थी. So what about these Navier-Lame's equations? Now the thing is, they're actually okay to solve. This equation is okay to solve. एक ये जो एग्जाम्पल मैं स्किप कर रही हूँ उसी में हम करके देख लेंगे. और ऑल्सो जो एग्जाम्पल दैट्स ऑलरेडी जस्ट पास्ट उसके अंदर भी इट वाज जस्ट द opposite version of it, but it was still something which was solvable. So the point is, this can be solved for simple problems, as is always the case with Navier-Stokes as well. लेकिन रियल वर्ल्ड मटीरियल्स थोड़े से ज़्यादा कॉम्प्लिकेटेड होते हैं, तो फिर उसकी वजह से टू सॉल्व द Navier-Lames equations we need certain numerical tools basically. So let me just discuss this very quickly. So there are two types of solutions that we can find. One is an exact solution, of course, जिसका मतलब ये कि आपने true solution निकाल ली है, and the other is of course an approximate solution. Exact solution का मतलब ये है कि जो आपने displacement find किया है ना, वो पूरी की पूरी body के ऊपर it's true. Whereas जो approximate solution होती है वो उसके अंदर the displacement field is only true at certain points, या फिर मे बी इवन किसी पे भी ना हो, लेकिन it's approximately close to the true value. ठीक. Now, as I said, we can find the exact solution to the Navier-Lames equation for simple problems, but most of the time, as soon as we get even slightly more complicated geometry, so for example, I was talking about the uniaxial behavior of this thing. ये तो simple है, इसका हम find कर सकते हैं exact solution. लेकिन consider करें कि मेरी beam साहब ऐसी होने के बजाय it was something with a sharp change in area suddenly. Even this now is something जिसका मैं exact solution नहीं find कर सकती. So you see how immediately as we get to real world objects and real world geometries and real world boundary conditions essentially, then our life is not so simple. ठीक. So वही बात जो fluids के अंदर होती है कि exact solution is only possible for very simple cases. Now comes to the approximate solution, which of course we're going to be interested in finding for real world problems. जैसे अब मुझे I want to find out कि कार के engine के वो piston के ऊपर क्या stresses लग रहे हैं. So वो piston की shape is already complicated enough. So for that, I'm only going to be able to find the approximate solution. So I need some methods to do that. Now, there are two types of methods. One is an analytical method. ठीक है जी. Analytical method के अंदर basically we're directly solving the problem with arithmetic and some maths. Whereas the other is the numerical methods. Now, numerical methods के अंदर there are even more approximations introduced, or what we tend to do is कि हम कोई, how do I put it, basically पूरी की पूरी problem को ना break down कर देते हैं into छोटा problems, and then we solve each of them to figure out the entire situation. So let me just give you an example. You remember we are able to find areas under curves, right? अब ज़ाहिर है there is an analytical way to find the area under this curve, which is just by integration. ठीक है, so integration करूँ so I'll find the analytical solution. Whereas if I use the trapezoid rule, अब I think कि सब लोगों को वो भी थोड़ा थोड़ा याद होगा, एक चीज़ होती थी trapezoid rule. That then is a numerical method, because उसमें ना I've broken down the problem a little bit further. Now, even between these, sometimes the analytical method gives us the exact answer, but very often even the analytical solution is actually just giving us an approximation. ठीक? So just note, whereas numerical is always going to give us the approximate solution. Okay, so just in this note, for us at this stage that we are at, because we look at complicated problems, it's the numerical tools and numerical approaches which are extremely important. ठीक? So I'm sure as you're doing courses here in your masters, you've seen that you have so many courses which involve numerical tools, such as, for example, आप लोग CFD कर रहे होंगे. Now CFD, computational fluid dynamics, that's based on a numerical method. And then for people who do solids, they may be doing finite element method, ठीक है, FEM. The finite element method is a numerical method. So we have to employ these CFT or finite element and so on किस्म के numerical methods because we're trying to look at complicated geometries. So as I said, all of these जो FEM, finite difference method, finite volume method, what else is there? There are many numerical methods which are used. So finite difference, finite element, boundary element, or there are loads others which I may not even know of. All of these are numerical methods. ठीक? There are designated courses for these, so I'm not going to discuss them any further. Even I think you're doing maths, you're doing numerical methods right now probably. I may be mistaken about that.
Yes, ma'am, कर रहे हैं हम.
Yes, exactly right. So वही बात आ जाती है कि to solve our Navier-Lames equations, we need to know these tools. We need to know many numerical methods in order to do that. ठीक, just quickly I do want to discuss some analytical methods only because we are not in this course, हम लोग कोई computational tools पे नहीं जा रहे. We're not going to be using an FEM code या फिर a FDM code and so on. So I just want to quickly introduce some of the analytical solution methods भी exist जो करते हैं क्योंकि हम लोग simple problems by hand analytically solve कर सकते हैं. So just to name some of them, there's the inverse method, there's the semi-inverse method, there's the method of, इसमें कोई हम, this is just extra for your information, because sometimes you will meet people जो ये they throw around these words कि जी मैंने inverse method use करके ये find कर लिया. आप कोई paper पढ़ रहे होंगे और उसके अंदर ये चीज़ आ जाएगी. अब obviously you need to know कि inverse method है क्या चीज़, right? So inverse method is something not very practical. Basically inverse method में आप क्या करते हैं कि आप ना you come up with solutions to displacement fields already. मतलब ये है कि आप पहले ही assume कर लेते हैं जी कि अच्छा अगर displacement u1 हुई e to the power of x1 plus something 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 and so on, and then you figure out, जिस तरह हम उस example में कर रहे थे, कि अगर मैं इसको apply करूँ into the Navier-Lames equations, then is it going to give me equilibrium या नहीं, and so on. So उससे फिर then you sort of figure out कि okay, if this is an equilibrium problem, then अब in the inverse direction you think about कि ये physically क्या चीज़ हो सकती है. मतलब ये कि आप पहले displacement, strain और stress से कोई mathematically abstract तरीके से कोई equations से शुरू किया और उसको फिर Navier-Lames use करते हुए सोचा कि ये physically क्या problem हो सकती है. Now this of course to me at least seems very counterintuitive. ये तो वो वाली बात हुई कि कोई केमिकल नया बनाने की कोशिश कर रहा और वो बस एक एक करके चीज़ें पहले एक का एक नंबर बढ़ाए, एक का एक नंबर बढ़ाए, एक का एक नंबर बढ़ाए एंड सो ऑन करके ट्राई करते जा रहे हो. So that's a different way of discovery, so to speak, right? So this is the inverse method, or as of course this is more common with mathematicians than with engineers because they're not really interested in what the physical problem is. They're just interested in the maths of it, and then later they figure out कि okay, ये physically हो क्या चीज़ सकती है, right? But इसके बरक्स there's something known as the semi-inverse method, and now this is something which is very common in engineering. इसमें क्या होता है कि you come up with unknowns for the displacement, stress and strain fields, sure, but साथ ही ना आप जो भी आपकी physical problem होती है आप उस पर सोच रहे होते हैं ताकि आपको उससे कोई hint मिल रहा हो कि ये किस किस्म की unknown function होगा. ठीक, so for example, if I was looking at my uniaxial deformation problem, then I can already come up with loads of things about the stress and strain field and the displacement field looking at this problem, right? Why? So for example, I can see के एक बात कि अगर ये uniaxial यूँ apply हो रहा है, so I can tell intuitively looking at the physical problem कि stress तो पूरा uniform होना चाहिए, There is no reason why the stress should be increasing or decreasing through this. It should be uniform. और क्या चीज़ इससे मुझे, हाँ, इस तरह फॉर एग्जांपल इफ़ आई वाज टू थिंक कि इसकी डिस्प्लेसमेंट फील्ड तो कोई एक्सपोनेंशियल फंक्शन होगा, दैट आल्सो मेक्स नो सेंस. क्यों इसकी डिस्प्लेसमेंट फील्ड, व्हाई वुड इट बी एक्सपोनेंशियल? इधर वो ज़ीरो है, इधर उसकी कोई वैल्यू है. सो टू मी इट मेक्स सेंस कि इट शुड जस्ट बी अ लिनियर फंक्शन, right? So my point is that in the semi-inverse method, you look at the physical problems, and from that you come up with some understanding of what the maths of it might be. Okay, and then you solve it. So that's just an introduction to this. As I said, this is just a little side extra discussion. There are other methods as well, such as the method of potentials, then the variational methods. Now this one you will encounter if you do the FEM course, finite element method, because the finite element method is based on the variational analytical approach. लेकिन वो है खुद numerical, वो इस पे based है सिर्फ. My point is, as with everything in continuum mechanics, there is another vast amount of knowledge out there, or if you are interested in different parts, and then, or if you ever need to solve one of these governing differential equations, then please you will have to look up that relevant part. ठीक है कि उसका उस particular problem का solve करने का क्या तरीका होगा. इस course में, अगले lecture में, we are just going to do a few examples of using the inverse method, only because हम सिर्फ इसी Navier-Lames equation को implement कैसे करना है वो देखने के लिए कुछ examples use करेंगे. Okay, but otherwise the solution methods are entire courses in their own, as I said, CFD, FEM, and so on. Okay, so I'm gonna end here, and then next week inshallah we'll do an example of solving a boundary value problem, or इसके अंदर we're gonna look at the basically the problem of waves going through a solid, that is koi vibrational waves and so on, passing through a solid basically. Or, and then the week after that we're going to move to fluids. So this one inshallah will just be short, and it'll just be the lecture next week, it'll just be demonstrating the use of the Navier-Lames equation.